Good evening. If you would like me to just get to the bloody point, please feel free to skip to the appropriate chapter. Otherwise, let me give you a short introduction. When asking about the 6502 microprocessor on the internet, you are often directed to the Visual6502 simulator to do your own research. And this is perfectly reasonable. After all, this is by far the most accurate simulation of the 6502 to date, simulating every single transistor and visualizing it at the silicon level. You could pretty much only get more accurate than this if you started simulating the individual analog characteristics of the circuit. But until somebody makes an electron level 6502 simulator, this is perfectly serviceable, I'd say. However, the problem is just this isn't really the most readable thing in the world in it. I mean, I think Frida said it best, but that's about where my understanding ends. So initially I avoided this because I thought I can't read this anyways. And fortunately there is a logic diagram available on archive.org now, and there's also of course Beregnyei's transistor level diagrams. However, ultimately, after working with those two, when I went back to this, I actually realized that I suddenly understood a little bit of what was going on. Now, there is a tutorial on NESDEV, I think it's worth pointing out, but I'm sorry to say that didn't really help at first either. Although after experimenting with this, after having looked at the logic and logic and transistor diagrams, I actually kinda also understand what the tutorial means a bit better, so I will reference it where appropriate. However, other than that, I thought perhaps there are people who, similarly to me, didn't really understand this diagram, didn't really know how to read this visualization, and so I thought it might be helpful to make a short, well, hopefully reasonably short example demonstration of how to understand this by going through a simple example, starting at the logic diagram, going to the transistor diagram, and then finally doing the mapping it to this visualization. So, without further ado, let us begin by looking at the logic diagram. Well, first of all, actually, before we do that, we have to find a suitable candidate for examination. I think a register would be a good candidate because that doesn't modify anything about the stuff it receives, it just has to hold it. And of course it would also be ideal if the component didn't have too many inputs and outputs, because that just makes it harder to understand, that just adds transistors. And the candidate I've selected is the X index register, because, oh, and by the way, this is the block diagram by Donald F. Hansen. It's fantastic. You could understand a lot about the way the processor works just from this without even having to go down any further, but if you do want to go down further, the nice thing about this is that the designations it uses match the original schematics, and that's because Hansen actually had access to original schematics when he made this. So what we can see here is the X index register is only connected to one bus, the SB, that's the special bus. The 6502 has several internal buses, but that doesn't really pertain to us in this example. But the point is it's just connected to one of them. And then it has one load line and one bus enable line. And as you can see, those are labeled SB/X, and the slash just means onto, and X onto SB. So it's always source onto destination. Pretty straightforward, I would say. So how do you find this in the actual schematic? Because, I've already mapped this out, but assuming you're just using the file of archive.org, and if you do, you should probably use the 13 megabyte non-text PDF because the other ones have reduced resolution. But anyways, if you have that, then how do you know where the X register is here? Well, the way I found it was by going up to this section where you conveniently have all the control lines laid out, and if it weren't already conveniently in plain sight, you would just have to scan these. You'd find it eventually, hopefully, and well, here it is. X onto SB and SB onto X. They're inverted actually here, but that's no problem because they get inverted again here. And so then we have the proper actual non-inverted lines. So we have X onto SB and SB onto X. And if we just follow those down, they eventually lead into these transistors. And so, your deduction skills will probably lead you to deduct that this line, if this line is X onto SB, and there's a transistor here which, as you know, will only let current pass through when it's powered, when the gate is powered, then this is probably the output onto what must be the special bus line, one of the special bus lines, and similarly then if this is SB onto X, well then this must be the input to this latch, this 1-bit latch, and this is repeated 8 times. So so that's how you know it's the 8-bit register, and so basically we've just found what we're interested in a 1-bit latch. So because this document is rather faded, and despite the high resolution, zooming in this far actually makes it pretty low res. And also because I actually got confused about the flow of electricity at first. I thought that it would go through here, but that it would also bypass that through here. I decided to make a slightly crisper reproduction, where I also took the liberty of adding arrows to indicate the flow of electricity. Now, this might make people who are used to drawing circuit diagrams properly cringe, because I guess this looks pretty dangerously similar to a diode when, except it doesn't have the line going across there. But I think for the purposes of illustrating this, it should hopefully be okay. So anyways, so this is a 1-bit latch. This is bit 0 of the X register, and I know it's bit 0 just because I happen to know that the bits go from 0 to 7 downwards, I think. But anyways, it doesn't matter which particular bit this is. In the visual simulator, it's also bit 0 is also on top, so we'll just so it's probably the same. Anyways, so right, so this is it. This is a binary latch. It's got an input and an output. How does it actually save anything? Well, let's just walk through it. So what if we want to save a 1 into this? Right now it's just in a 0 state, everything's off. Well, for a start we'd of course need a 1 on the special bus. So that's on. And then in order for this to actually get in here, of course we need to power this SB onto X transistor, which will power the input gate. So by applying currents to this, that then makes this transistor conduct, so the electricity can go through here as guided by my beautifully steady hand, and then it reaches this point. This is just a double inverter. It might look weird having the circle at the input of the inverter rather than the output side, but I just copied the notation used here. You can see it a bit more clearly on the Y register here. This is just a shorthand, I guess, just to make it immediately obvious which state you expect the line to be in relation to be to the original input, if you will. You know, it doesn't matter much here anyways because they're directly chained. And so, you know, we've got this double inverter. And the reason we've got this here, because you might wonder, well, what's this for? If it's just going to come out the same way it came in, why even have this? The reason, at least to the best of my understanding, is just for refreshing the signal. Because if it's coming in from a special bus, then it might be quite weakened by the time it gets here. You know, it might not be a nice, steady, unambiguous 5 volts. Or at least, you know, I guess it should still be fairly unambiguous, but still, it's a good idea to refresh it. And so instead of just putting it in directly, it controls a NOT gate, which basically has its own power supply. And because, of course, we don't actually want to invert it, we just invert it again, and then we get this output. Right. And then, of course, and by the way, fun trivia fact, in the unlikely events that you've ever heard of the obscure hidden gem known as Minecraft, this is literally how people used to build redstone repeaters before they were turned into their own block. So what you know, educational Minecraft. Anyways, and then of course this output here can go back to the latch output, which would then allow it to go on back onto the special bus if this line were high. But crucially, the way it remembers this is it also goes into this feedback loop here. And you know, then if it just go, and you know, then of course if it just goes through this here back into here, well, it's just looping in on itself. It's constantly being refreshed. I guess that's another reason, because eventually it would just find its way to ground somehow, because nothing's a perfect insulator. But you know, this way it just gets continuously refreshed. And of course, to be able to go here, this transistor needs to be enabled. And right now it's disabled because this is enabled, or rather because the processor makes sure this is only ever enabled if this is disabled. Why? Well, first of all, what even is this? It says Phi2 here, and that is just the one of the 2 internal clocks of the 6502. It's effectively the same as the external clock. There's also Phi1, which is inverted, and so this basically means that this transistor only ever conducts every other half cycle, so for half of every clock cycle. And so, if we want to complete this circuit, well, then we have to wait for this to turn high, which will then, you know, if that happens, this will then conduct, so we'll turn this high. And at the same time, the processor will make sure to disable, this input here. So now the latch is just feeding itself. And one might wonder, well, what does it do this for? That is, why does it interrupt this signal every half cycle? How does that even work? Let me just get rid of that. Well, the reason for that is because we need some window of opportunity to override this. Because now, of course, we're saving a 1 here. And by the way, under normal circumstances, by the way, when this is low and there's already a 1 in here, I guess the residual electricity just lingers for long enough that it doesn't reset to 0. But the problem is, what if we then want to set this back to 0? I mean, if we just try to set this to 0, this 1 would overpower it, wouldn't it? We would have no way of overpowering this already present signal, and that's what this is for. Because when this is off, again, under normal circumstances, if we just disconnect this, under normal circumstances, I guess the electricity just lingers long enough that this doesn't automatically reset. In fact, that appears to be the reason why the 6502, the original one anyways, why it would lose register contents if it were halted for too long, because eventually this electricity would still dissipate, and so it can only hold this high for so long, for half a clock cycle approximately, maybe a bit longer, and so it needs to be constantly re-enabled. That's my understanding of it anyways. Feel free to correct me if I've misunderstood this. But anyways, so if this isn't so under normal circumstances, this holds the charge just long enough that it can refresh every half cycle. But the nice thing about this is, if this is off and this is interrupted, and we then go ahead and and by the way, and the bus then happens to be 0, and we go ahead and re-enable this, so activate this, well then this is effectively tied to ground. I guess whichever residual current is here just gets drained to ground via the special bus. I mean, yes, it has to go backwards through this transistor, but I read in passing on a Stack Exchange answer that apparently technically that is possible. It's not as easy, but we're not dealing with a constant supply of current here either. And so this residual electricity drains, and because there's nothing coming from here, because this is blocked, that then goes into here, which inverted to a 1, which inverted back to a 0, and that then turns this into 0. And we'll see in the transistor version that how this then actually drains any residual currents here. But on this level, it's sufficient to know that it then just gets set to 0, right? And then of course, once we then later on the next half cycle close this and re-enable this, it's just going to constantly feed 0 back in on itself. So I think that's I hope that didn't make it more confusing than it was before. Yeah, and of course, if we wanted to output what was currently in this bit, then we would toggle this line, or enable this line. But I think that's pretty straightforward. All right. Now, for this next section, you may want to skip this and go to the next chapter if you haven't read Beregnyei's Guideline to Reverse Engineering, because this may confuse you unnecessarily if you haven't read this. But if you have read this and maybe you were confused like I was, it might be a good idea to get us on the same page about something here. And that's, if we scroll down here, there seems to be a bit of a confusion in terms of terms. So first, this guide explains that, implies that this is an enhancement mode transistor and this is a depletion mode transistor. I added those labels; those weren't originally there, but that makes sense. In fact, doing some other research, I then found a Stack Exchange answer that seemed to confirm that this is an old-fashioned shorthand for a depletion mode transistor. So fair enough, that all makes sense. And then we have this example inversion circuit. And again, we've got a depletion mode transistor up here and an enhancement mode transistor up here. If you work this through mentally, it would make sense. But then description here might, at least it briefly confused me. It briefly got me off track. Let's just read it together. The essence of the operation of the inverter as a 2-transistor switch is whether the lower driver transistor, so this one here, pulls down output to 0 potential or not. This depends on the input. If the input is a logical 1, the driver opens. That makes sense. That's just the behavior of a regular transistor we've known so far. So that's just the regular of an enhancement mode transistor. Oh, and right. And so this regular transistor, as I just called it, is an enhancement mode transistor, and a depletion mode transistor, I think it's worth explaining, is the opposite. That is by default always open, and if you apply current to the gate, it closes. And That is, it blocks the flow of electricity. I think this whole opens and closes terminology, in my opinion, seems a bit unfortunate, because what they mean here is it opens, that is, it conducts, and it closes means it blocks. But you could also, if you think of it as a switch, well then closing a switch would mean closing the circuit, and opening it would mean breaking the circuit. But granted, maybe that's just me splitting hairs there. That's actually why I marked this part in orange. Anyways, so yeah, the driver opens if the input is a logical 1. That is, it forms a short circuit between the output and the ground. Thus the output becomes a logical 0. So far so good. Right, then if the input is 0, the driver transistor is closed as if it was not there at all. Again, my opinion, I don't like this choice of words, but it makes sense, that, yeah, if this input is 0, then this no longer conducts, and so it's no longer pulled to ground. So yeah, in this case the output becomes 1, and here is where it gets confusing, because then it says in this case the output becomes 1 through enhancement mode transistor, since this is always open due to gate source connection. I mean, two things. Originally I wanted to go into much more detail about why it wouldn't make sense for this to be an enhancement mode transistor, but by this point I'm pretty confident that this is in fact the symbol for a depletion mode transistor, so I think that was just the term being mixed up. And in fact, the gate source connection, if you connect, and I just know this from a bit of googling, I'm not an electrical engineer, but if you connect the gate and source of a transistor, that apparently just makes it perpetually off, which in this case, if open means it conducts, then an enhancement mode transistor would always be closed if you connect the gate and source. A depletion mode transistor, like here, would always be conducting if you turn it perpetually off. So I think that's another sign that it would be a depletion mode transistor. But on an entirely separate note, I actually think now that this isn't a gate source connection at all. This looks like a gate drain connection. I mean, you'd think that this would be the input, right? And then it would just, and then this here would be the output. So this would be the source and this would be the drain. And in fact, apparently the 6502 actually does use this also in other places. This is called a transistor, and specifically a depletion mode transistor with a connected drain and gate, is called a diode connected transistor, and it basically just acts like a resistive load. So, in a nutshell, this is what we consider a pull-up. Or we could consider this just a pull-up resistor. For our purposes, it doesn't matter. It's always, it's always short. Short. It always has the gate and drain connected. So for our purposes, this is just a pull-up resistor. We can just treat this as our power source. Alright, so to summarize again, these are depletion mode transistors, and they are connected at the drain and gate. The drain and gate are connected together, and this is an enhancement mode transistor. I at least am pretty certain that this guide may have mixed that up. Okay. Oh, I've already zoomed in, but let's take a bird's eye view first. Either you followed me here or you skipped here, and at any rate we're now going to look at Beregnyei's very helpful transistor level schematic of the 6502. This is from a Rockwell model, but that doesn't really matter for our use case. Either it was drawn rotated 180 degrees, or maybe the Rockwell chips actually are rotated 180 degrees, because if you look at this section here, this fairly how do you say, distinct section is the PLA, and I'm just saying that because that's what it looks like. That's what the PLA looks like. For instance, also on this schematic, you can see here all these lines, all these crosses of lines with dots in them. That's basically what this here is as well. So to find the X register, if we knew that it was on the left in the original diagram, logically it would be on the right here, and we don't have to spend a lot of effort at all. in finding this because it's conveniently labeled right here. So xreg, that's this. And so we've got all the 8 bits of the X register here, and we can zoom in. So this is 1 bit of the X register on the transistor level. Once again, I've copied this diagram and slightly adapted the syntax because I felt it might be helpful not only to have the arrows, but also to explicitly label any connections. I guess it's probably a convention that in circuit diagrams diagonal paths can never be connected, and perpendicular paths are then probably always connected. But I felt it couldn't hurt to make this explicit. So, and also I changed the designations here to match the other diagrams, and so this is the result of that. Note that due to the chip being flipped, the lines too have been flipped, so now the input is on this side and the output is on this side. So this is the transistor level diagram. Now, if you haven't watched the previous section, you won't know yet what these big fat things are, and in fact, I myself, when I first saw these in diagrams, I couldn't find out what they were. Again, I only happened upon a confirmation for what I thought by browsing through the guidelines and then on a Stack Overflow or Stack Exchange answer. But anyways, this is called a depletion mode transistor, and this is basically just a transistor behaving the opposite way. So normally transistors conduct only when there's current on the gate. In this case, it conducts unless there is current on the gate. With that being said, for our purposes, we don't really care about this thing's behavior at all, because the drain is connected to the gate, and a depletion mode transistor with the gate and drain connected is called a diode connected transistor, and that just acts as a resistive load. So I guess you could say, for our purposes, this is just a pull-up resistor, or simpler yet, it's just a power source. So basically, the takeaway is there's always power here, no matter what. Okay, so how does this translate to what we've seen before? This is the exact same thing, just broken down to a lower level. I mean, for starters, of course, we have to get this thing into its actual initial state, because we now have the transistors here supplying power in places. So let's just work through what this would be like, before we introduce any values from the bus. Let's see. So this value here, or rather, once again, we're 0 at first, and this here is the output line, and if we follow that in this direction, this is 0 here, and so this transistor here doesn't conduct, which means that because there's always power from here, but it can't get through here to ground, it instead flows through this line into the gate of this transistor. And yes, technically it also flows into here, but we don't care about that. Anyways, so it flows onto this transistor, and that allows it to conduct current. And because we've got current coming from here, in this case, it can just go to ground. And because it can go to ground, there's no reason for it to go anywhere else, right? So, because electricity always wants to go to ground. So these lines just stay off. And so with every half cycle, we just, allow nothing, a bit of nothing to pass through here, and so this won't change, this whole state. So this is basically the 0 state. Then what happens if we set it to 1? Well, once again, we've got 1 on the bus, and we'll enable the SB onto X line, and that will allow this 1 to travel into this transistor, and now this will conduct, and so the current here can go to ground, which then means that it drains away from this line. Being able to increase the eraser size would be nice. But anyways, so now this is unpowered, which means that this transistor will block. And so now this can no longer go to ground. And so instead it will go everywhere else. It will go to the output. It will go to here, as little as we care. And it will go here where it's currently blocked by the Phi2 transistor. And then once again, with the next half cycle, simultaneously this transistor will close, and we'll assume this can also go away now from the bus. And at the same time this will open, allowing currents to flow through here, maintaining this state. So just like before, now we've latched the 1. And similarly, just like before, if we want to now reset this latch from the bus, well, once again, first the Phi2 transistor has to be off, so it has to block. So now power isn't going through here. Once again, at this point, if this weren't active, I guess the current would just linger for long enough that this doesn't just reset. However, because we've opened, we'll open this transistor here, and thus, this is pulled to ground. This SB line is actually pulled to ground. So again, my suspicion is that this, or my hypothesis, if you will, is just that this then drains to ground via the SB line, given that there isn't much current here to begin with. And then, of course, once again, when this turns off, now this can no longer connect to ground, and so I won't bother going to this gate again. But you can imagine that. But yeah, it will power this transistor, which will then let power go to ground here again, which will then drain any current, any residual current on this line, or indeed on this line. And so now we're back in the zero state. And again, on the next half cycle, we'll just close this input. Yeah, I probably shouldn't say close and open either, but yeah, and this will maintain the nothingness. Only half an hour. Wow. Okay. Right. But I think this is important for actually understanding what's going on at the silicon level, which we will look at now. So let me quickly go back to this. Alright, the moment you've been waiting for, or the moment you couldn't wait for, depending on whether you followed me here or skipped through, how do we actually make sense of the blinking lights now? Well, first of all, of course, we have to find the piece we're interested in, which was the X register. Fortunately for us, the original logic diagram maps, at least almost exactly, maybe actually exactly, to the silicon of the chip. Now, the page 2 of this diagram is actually the upper half, but that's not a problem. We can see the distinctive look of the PLA here. And as you can see, that just about looks the same. At least that looks different than much of the other stuff, this grid here. And so by that logic, if we found the X register on the left side of the bottom half, that would mean it would be somewhere around this area. So we'll just zoom in and click around a little bit until we find it. Okay. Now again, I'm sort of here on the left side, and of course I already knew where it was, but you know, I don't think there's much value in showing me searching for half an hour. Didn't take that long, but you know, still. Anyways, and then if we look closer, actually, let me zoom out a little bit. We can see here these very similar shapes, of which there seem to be 8 in a row. Or actually 8 in a column. And if we zoom in a little bit more on these, we're starting to see a shape that kinda sorta resembles what we saw in the logic diagram earlier. And now we can click on these lines here, and you know, we can see here it actually says SBX, SB onto X. We've just found bit 0 of the X register, and X onto SB. Now before we continue, I guess first a note on the syntax here. The violet stuff, I guess it's violet, I looked up the colors before, but is the silicon. And when that turns like, I guess, magenta, purple, dark pink, just when that turns reddish, more reddish than before, then that means it's powered, right? So if it's this violet, if it's this cooler color, then it's off, and if it's this redder color, this hotter color, this warmer color, it's on. So that's the silicon, and that's what the gates are made of, and that's what can block the flow of electricity. Then the red stuff, that's just 5 volts, that's power, and the green stuff is ground. So as you can see, these are areas here rather than simple lines, but the principle is the same. And the yellow, what yellow means is that it's basically it's grounded, and orange means it's not grounded. So I mean, there's power on both of these, but in the yellow case it's just immediately going to ground, and in the orange case it's not currently going to ground. So you could also consider the yellow as the 0 and the orange as the 1. So right now, bit 0 of the X register is in fact set to 0. Yeah. Right. What else? Well, if we look at the silicon structures here, we can see, and you know, if we click on this is SBX, and there's something overlaid here, but there is this orange line here, which appears to go into the bit 0 latch through this purple, through this violet silicon here. So it stands to reason that that is actually the gate of the SB onto X transistor, you know, just as one long silicon string rather than a discrete component. And conversely, this is the output transistor. If we step the simulator a bit, we'll quickly see that this line here constantly pulses on and off every time I click this. This simulator actually simulates every half cycle, which makes it pretty easy to see this. So it will probably not surprise you to learn that this is actually the clock controlled pin. This silicon is apparently called C clock. I'm not sure what the C stands for, but whatever, it's Phi2 is what it is. So these are the inputs. Now, how does this work then? How do we actually know? How does this actually manage to store the 0 here? Well, these areas, these yellow and orange areas, can actually control some of the silicon. Specifically, you can see here the silicon sort of reaches into this area. It's sort of surrounded by it, and that's usually a good indicator that that's actually toggling this. In fact, you can click on this to see that it's connected. So this yellow area is connected electrically to this silicon, which means that it's controlling this as a gate. And because it's yellow, because it is effectively 0, right? Because it's it's effectively 0. This gate is blocking, which means that whatever is here, it's this orange stuff, there is current here too, and it would like to go to ground, but it can't because this silicon is blocking it. And the black stuff is basically the insulator. Yeah, the NESDEV tutorial doesn't specify if that's supposed to be anything specific. I guess that's just air, because you've also got grey stuff, like maybe this stuff that's just metal. But anyways, that's not interesting. The point is, this could only go to ground via this silicon, and because this is currently off, so non-conducting, that means this has to stay on. It has to stay of 1. Okay, so far so good. Then this interesting construction here is actually described in the circuit tutorial. So you can see here this sort of, it uses slightly different terms for these colors. It describes here what a transistor is like. That's basically what we saw here. So this is the source. In our case, the source actually has power at it, but it's closed because the gate is blocking it from going to the drain, which is ground in our case. And then it describes here something called a power source, and it mentions that this is a distinctive hook shape. And as you can see here, what that has is it has a source, which is in this case 5 volts. And then this is apparently a depletion mode transistor. It mentions that it doesn't actually look any different on the visual simulator, but we just know that. And this is the drain here, and you can see here it's not actually as distinct here as it is on the Visual6502, but this drain here then also applies current to this gate. And we see this here. This is our source. This is power, 5 volts. And then it goes through this silicon into this area. So this is the drain. And then the drain controls this silicon of this transistor. And so, yeah, that's basically what we saw earlier with a depletion mode transistor. That's actually just a pull-up resistor, essentially. We also see this here, by the way. This powered section, this 5 volt section, goes through this violet silicon into this area here, which in turn controls this. However, this isn't as interesting because this is purely a diode connected transistor, while here this is actually more than that, because if you notice, it also got this line going off here, and this is also described in the tutorial here as an inverter. So we can see here once again you've got this source, the 5 volts going into the source, a drain that, and this is connected as an NMOS. And we've also got the input here, so of the inverter. So this in this diagram plays the role of this in the Visual6502 simulation we're looking at right now. Right, it's connected. So this is the input basically to this inverter, and this here is the output. You can see it branching off from this diode connected transistor. And the cool thing about this is this basically combines the two functionalities into one. So more or less you could argue this is both acting as the pull-up, as the diode connected transistor to work as a pull-up resistor, but it's also actually controlling the inversion here, because this power here will then go through here, and because this is being powered by this section, that means that this area here can drain to ground, right? Once again, it can only go to ground via this silicon. The black sections here are just air, so they won't let anything pass. And so, because this can only go, because this can go to ground, it will go to ground, which means that the entire section is grounded and therefore 0. And then we've got the clock pin just blocking this once again every half cycle. And whenever it gets through, of course, well, we just get the grounded potential going through. Okay, now let's step through this program. Let's actually reset it. So the code isn't terribly interesting. First we're loading a immediate with 0 for some reason. Then we're jumping to a subroutine which will conveniently increment x and decrement y. And so we will see this changing from 0 to 1. So let's investigate this. It will constantly reselect. Well, then let me select something completely different there. Or maybe the clock. That's even better. So we'll just step through this until we get to the subroutine. So as you can see, it jumps to subroutine at 0010. Remember, little in Endian notation. Okay. Now, actually, let me select something completely different this time. The E8 is the increment x, and we'll just step this until something interesting happens here, specifically until it loads the value from x onto the bus, which should only be a matter of a few cycles. There we go, half cycles. You can see here, this enables the x onto SB line, which now lets the value of currently stored in x go onto the bus. And then it's going to go to the ALU to be incremented. So we'll simply step this. Nothing happens yet. Notice that this was off when we loaded x onto the bus, and now it's on again to refresh this. Right, and now it's off again, and now we're putting the value from the bus, which is 1, right, because we incremented 0 to 1, which sets bit 0. That now gets put back into the register. So this is now powered, which lets this 1 from the bus go through here, and that then powers this this gate now, right? Which lets the source here, this yellow area, drain to ground. That then causes this to be pulled low, and that doesn't really have an effect on the 5 volts getting through, because again, diode connected. But what it does have an effect on is this thing no longer letting current through. So when 5 volts goes through here now, it can't go to ground, and so it will instead have to go everywhere else. And then when we step this once again, this now stays in there. This will just keep refreshing itself. Now, I will step through this a few times. This just runs that subroutine in an endless loop. For C is a jump absolute instruction, and then it just jumps to address 0002, so here, and that just jumps to the JSR then. So now we'll see it reset this bit. Okay, we're once again at the increment x. This will increment x from 1 to 2, which means bit 0 will be cleared and bit 1 will be set. So if we step this through again, once again, we see the value in this x bit 0 being put onto the special bus. I hope I always called it the special bus previously, but yeah. Anyways, and then when we step 2 more half cycles, so now nothing's happening because the ALU has to increment it, and then when we step once again, now the 0 on the special bus is allowed by this transistor to pass into, by this silicon being powered. This silicon is powered, so now the value from the special bus can get in here, at the same time, you know, it's already gone here, but at the same time, the orange section that used to be here couldn't get into here because it was blocked by this silicon, controlled by the clock pin, or by the clock signal rather. So this drains, again, I would guess this just drains to ground via the special bus, which causes this transistor no longer to conduct, which then means that this can no longer go to ground, so it becomes orange, right? It becomes a 1 basically, which then means it powers this again, which has no effect on the plus 5 volts getting here, but it does have an effect upon the output of this inverter, which will now no longer let current through. Sorry. Which will now let current through. And then, of course, whichever orange current used to be here, whichever 1, if you will, well, that all just drained through here into ground, and so now it will stay as 0. I hope I didn't misspeak like that at other times without noticing it. That would suck. Well, yeah. And of course, and you can see here now bit 1 of X is actually set to 1. And similarly here, Y is set to -2. And so that means all the bits except bit 0 are set, which does look like what's happened here. Okay, so hopefully this helped you understand this visualization a bit better. It only took 52 minutes, so again, if you have any feedback upon this, then please feel free, or if you have any further questions, also feel free to let me know in the comments below. Otherwise, there's a link. I will provide a list of links to the materials used in this tutorial, so you can follow along if you wish to, or just so you know where you can get this stuff. And well, I thank you for your attention. I hope you didn't fall asleep, and well, I am looking forward to your comments on this. Goodbye.